we ended our previous video by showing that EY satisfies this equation. And what we're going to do in this video is convince ourselves that this equation describes a wave moving in the x direction. But let me first remind you how we got here. We started with Maxwell's equations in vacuum, in particular Faraday's law and Ampere-Maxwell. No charges, no currents, so in vacuum. And we decided to look for solutions in which there was a non-zero EY and a non-zero BZ. And those EYs and BZs were constant along planes in the YZ direction, but EY and BZ would have one value on this plane, and then another value on this plane, and then another value on this plane. So EY and BZ would depend on x, and we've seen that such a pattern can't be stationary. And we're now going to see that, in fact, the whole pattern is moving in the x direction as a wave. So from Ampere-Maxwell, using some red rectangles and applying Ampere-Maxwell quite directly, we first of all derived these first-order differential equations, which had a d by dt and a d by dx in them, but only one derivative. But each equation mixed up together EY and BZ. We then manipulated those two equations and we got two new equations. This was one of them. So this equation is nice in that it has only EY in it. It's now second order in derivatives, d squared x by a dx squared and d squared by dt squared. We then got another equation, exactly the same form. I'm not writing it today, but remember that we have another equation that is exactly the same form but with a BZ here. So EY and BZ both satisfy the same equation, and I now want to convince you that this is a wave equation. So the way I'm going to convince you of this is I am going to show you that if I choose EY to be any function of x minus vt, I've solved the equation. So the calculus to show this to you we'll do in a second, but let me first explain what I mean here. So what I'm saying is that if I choose EY to be the sine of x minus vt, it's going to satisfy the equation. Well, I better tell you what v is. There might be something to talk about there. But for a particular choice of v that we're going to get to very soon, this will satisfy the equation. But so will this. That satisfies the equation also. So will this. Sine to the 17th power of x minus vt plus cos to the 12th power of x minus vt. That'll satisfy the equation too. Any function of I claim that any function of x minus vt, any generic function of x minus vt, will satisfy this equation as long as I pick the correct value of v. And that's what I want to show you now. So I want to show that this satisfies the equation. So let me now rewrite the equation. And so let's evaluate, actually let's do it this way. Let's evaluate the left-hand side. So d squared by dx squared of EY. If EY is f of x minus vt, what happens when I differentiate twice with respect to x? Well, I'll pick up, what I'll get is f double prime of x minus vt. Now what do I mean by this? F is a function of an argument. I'm differentiating f with respect to its argument twice, and then I evaluate the new function that I've gotten by differentiating twice. So if I had sine differentiate twice, I would get cos, I would get minus cos and then minus sine. If I had sine to the 17th, I have to do more work to differentiate twice. But differentiate sine to the 17th twice. And I have a new function, f double prime. Evaluate that new function at x minus vt, and that's what I have on the left-hand side. Now what about on the right-hand side? On the right-hand side, well, I have mu naught epsilon naught d squared by dt squared of EY. And what's that equal to? Well, it's mu naught epsilon naught. And then I have to take two derivatives of this now with respect to time. So when I differentiate this with respect to time, what's the argument of this function is being set equal to x minus vt. That just has an x in it, and when I differentiate the argument with respect to x, I just got a 1. But now the way t is sitting here, it's multiplied by minus v. So according to the chain rule from calculus, when I differentiate this twice with respect to time, I'm going to get 2 powers of minus v. So I get minus v quantity squared times the second derivative of this function evaluated at the argument x minus vt. So I have a function f, it has an argument, differentiate with respect to that argument twice, evaluate the new function that I just got, evaluate it at x minus vt, and multiply by minus v twice. So, have I satisfied the equation? Well, this equation, which came to us from Maxwell's equations, from Ampere-Maxwell plus Faraday, manipulated in the way that we saw in previous videos, this equation will be satisfied if this equals this. And what you see is that this equation is satisfied if and only if. So the equation that I started with is satisfied if and only if v squared is equal to 1 over mu naught epsilon naught. Or I can rewrite this as v is equal to 1 over the square root of mu naught times epsilon naught. So I have a solution to the equation if and only if I pick the right value of v, and the right value of v is 1 over the square root of mu naught times epsilon naught. Now, what does it mean to have a function of x minus vt? So let's think about what it means for EY to be a function of x minus vt. So let's start at time 0. I have some pattern at time 0. My EY takes on a certain value at this x at time 0. Okay? So EY has some pattern. Those yellow arrows have some pattern. And at time 0, EY has a particular value at this location in x, at this plane. Now let's go to a little time later. Let's go to time t, where t is some positive number. And if I'll ask myself, where is the x where this function has the same value that it did here at t equals 0? So it had some value right here when t was 0. That means I need to find the x where x minus vt, has the same value that x used to have at time 0. So, and that means I have to go to the right a distance vt. Okay? So at time 0, f had some value here. At time t later, f will have that same value over here, vt to the right. And then if I go to a later time, let's say t2, I have to go vt2 to the right from my original point to get to the place where f has the same value that it had here on this plane at time 0. So at time 0, f had some value here. At time t1, it has a value of vt1 over to the right. At time t2, it has that same value vt2 over to the right. And so what you see is that the fact that EY is given by a function of x minus vt means that whatever the pattern of EY is, it's moving in the x direction with speed v. So I have a wave solution traveling in the x direction with speed v, and the equations, Maxwell's equations, have told me the value of this speed. And this was Maxwell's great discovery. He started with equations that had been derived by people before him, starting from Coulomb's law, which had electric forces between charged objects, and that's where epsilon naught comes from. Where did mu naught come from? Well, that came from Ampere. Mu naught came from magnetic fields made by currents. So epsilon naught came from charges and Coulomb's law. Mu naught came from currents and Ampere's law. And Maxwell made the remarkable discovery that when he looked for solutions with no charges and no currents, he found that those solutions describe waves moving with a speed given by this value. And well, so he then, he knew what mu naught and epsilon naught were, and he calculated what speed are these. My equations tell me waves moving with a speed. What's the speed? And he worked it out, and he didn't have as accurate measurements of mu naught and epsilon naught as we do today, but he worked it out, and I will give you today's value. Today's value for the speed is 299,792,458 meters per second. So it's about 300 million meters per second. It's about 300,000 kilometers per second. So Maxwell started from laws describing forces between charges, epsilon naught. Laws describing magnetic fields made by currents, mu naught. Got rid of the currents, got rid of the charges, and found that his equations with no charges and no currents described waves moving in the x direction with a speed that he recognized, because he noticed that the speed that he got was completely consistent with being the speed of light. And this was Maxwell's greatest discovery. This was one of the biggest examples in science of getting out more than you put in, where when you succeed in finding a rigorous and fundamental description of a set of natural phenomena, in this case electric forces and currents, once you have that fundamental description of an aspect of nature, more comes out of it than you expected, because nature connects different phenomena to each other, which you didn't know about until you found the fundamental description of, in this case, electric and magnetic forces. And from that fundamental description, you get waves moving with a speed, which we now call c, the speed of light. So Maxwell discovered that his equations had wave solutions moving at the speed of light. About 20 years later, a physicist named Heinrich Hertz learned how to make such solutions, and he made what we now call radio waves. But light waves, we now understand, and in fact Maxwell guessed, and he was absolutely right, light waves themselves are electromagnetic waves. So are X-rays, so are gamma rays. What's the difference between radio waves, X-rays, gamma rays? Well, it's the choice of this function f. You make one choice for how this f varies with x at time t, so how the yellow arrows are varying with x at time t, and that's a light wave. You make a different choice, it's a radio wave. You make a different choice, it's an X-ray. And in fact, what matters for whether you have a radio wave or a light wave or an X-ray is the wavelength. The radio waves have the longest wavelength, so the yellow arrow, the wavelength of the pattern is very, very long. Light shorter, X-rays even shorter. We'll get to all of that and more. But I want to end today, first of all, by commenting further on the way we think about this today and how we define units today. Today, actually, the way we define units is to make this actually a fundamental definition. So this, in fact, in today's units, this ends with a decimal point here, and there's nothing after the decimal point. This is not a measured quantity. This is now a defined quantity. The way we define units today is we define the second in terms of a fundamental atomic physics process. The fundamental unit of time is described in terms of a process that occurs in individual atoms. And from the measured value of the second, we use this definition for the speed of light to define what we mean by the meter. That's the modern way of defining the modern way of defining the meter comes by making this your definition of c. Mu naught, if you'll remember from many videos ago, mu naught is defined to be 4 pi times 10 to the minus 9 in our unit, so it's newtons second squared per Coulomb. And as we discussed back then, this choice, this definition corresponds to picking our units of charge. So we chose our definition, our units for time from some fundamental atomic physics process that defined the second. This defines the meter. This defines the coulomb. And then epsilon naught is given in terms of the other quantities by 1 over c squared times mu naught. And that epsilon naught agrees with the numerical value of epsilon naught that I gave you way back at the beginning when we did Coulomb's law. So that's the modern way of defining them, but it's completely the opposite of the historical way. Historically, what happened was people going back to Coulomb started measuring epsilon naught. People going back to Ampere started measuring mu naught. Maxwell then came along and said, hang on a second, these equations have wave solutions, but the waves are traveling with a particular speed, and that speed is 1 over square root of mu naught times epsilon naught. And he then noticed that this speed is, in fact, the same as the speed of light. And later, Hertz and many others learned how to make these waves, study them quantitatively, and we're going to describe all of that further as we go along.